Victoria Horan-Golibar is currently Global Head of Technical Sales. She joined the sales team at D-Wave Systems in 2018. In her current role, Dr. Golibar works with teams around the world to bring quantum annealing to a variety of groups through seminars, workshops, and conferences. She received her PhD in discrete mathematics from Arizona State University in 2012 through the SMART scholarship program, and more recently completed a MS degree in computer science with a specialization in machine learning at Georgia Tech. Her doctoral research breached both mathematics and computer science with a focus on de Bruijn sequences and gray codes for combinatorial objects. Victoria, we're looking forward to your talk.
All right, yeah, so my background is not in computer vision, so I do not have a ton of experience in that area. As was mentioned, so my background is in discrete math and computer science, so I've been at D-Wave for a little over 5 years. I do a lot of our technical training, tutorials, workshops, kind of tracking different applications and use cases on our platform. So today I thought I'd primarily just kind of give an overview of what D-Wave has available, kind of where we've come from, and a little bit about what our system looks like. Happy to take any questions throughout or at the end as we go through. Hopefully this isn't it's not too marketing or fluffy for you all, but we'll see how it goes. So as we've heard, there's kind of two different models of quantum computing out there, and they are very, very different, both in applications and how you use them. So D-Wave right now offers quantum annealing. We are also building a gate model system that will be available in the future. So we really view it as, there's space for both of these models. They are very different to use. As you can see here from some of the applications that are listed, they have their own strengths and weaknesses on both sides. So annealing is really what I'm here to talk about today. It's definitely the most scaled up that you'll see available. I view it as the easiest to use and get started. It's got a lot of really relevant applications, both in computer vision and in industry. So we work with a lot of different groups on a ton of different things. So these are just some of the examples of different problems that we've seen people working in. So things like scheduling, routing, all of those sorts of like combinatorial optimization problems tend to be really, really good fits for quantum annealing. So this is the very hand-wavy explanation for those of you that are here and are kind of brand new to quantum annealing. Really what we like to think about this is as if you have a landscape, which you can think of as like a cost function, something that you're trying to minimize. So you've got an objective, which is your cost that you're trying to minimize, and you've got constraints which kind of determine which of those solutions are feasible or not. And really what we want to do is we want to explore that whole landscape to find the lowest value, the minimum. That's what quantum annealing is really doing. And whereas your classical algorithms are kind of going to be sequential, looking throughout that space, quantum annealing is going to use quantum effects like tunneling, superposition, entanglement to really search through that space very efficiently, very quickly, and kind of simultaneously. That is a very hand-wavy, non-technical description of what it is, but it's a nice mental picture to kind of imagine like what quantum annealing is doing. It's using those natural effects to minimize. So at a glance, D-Wave has been around for quite a while. We are local to here in Vancouver. So we were founded in 1999. We've really been working in this space for a long time. Our office is about 20 minutes from here. That's where our labs are. We have a huge R&D component in our company, and we work with a lot of commercial customers as well as academics around the world. We have a lot of different use cases, a lot of different offerings, which I'll talk about in a minute. So there was a question earlier about like, how do you access these? Not everyone has a quantum computer like in their office. And so this is a little bit of what we do have available. So Advantage is our largest, most performant quantum computer that's available right now. It has over 5,000 qubits. This is our 5th generation quantum computer. We've had everything from 1 to 2 qubits scaled up through time since 1999 to where we are today. This is all offered through a cloud platform called Leap. So LEAP is completely in your web browser. Anyone in, our LEAP countries can go and sign up for free. So if you wanted to try it out, you want to see what the environment looks like, what the software tools look like, anyone can access that there. And, it's available with real-time access almost every day. We have small maintenance windows throughout the year, but the majority of the time it's up and online and ready to be used. We have a bunch of different quantum computers, actually. We don't just have one. So we have our Advantage system that's online for everyone to use, that's in our lab, like I mentioned, 20 minutes from here. We also have one in Southern California, and we have one in Germany at the Jülich Supercomputing Center. We also have online a prototype of our next generation system, which I'll talk about a little bit more, as well as a whole suite of hybrid solvers that are available for larger, more real world size problems. So as you can imagine, with 5,000 qubits, for some problems, 5,000 is a large number of variables, but for many in the real world, that's a really small number of variables that you can use up very quickly. So these hybrid solvers allow you to run problems with up to 1 million variables. So when you're thinking about, real world problems in these formulations with binary variables, these really allow you to scale up and really see what you can do with these hybrid algorithms. The next circle is Ocean. So Ocean is our Python tool suite. So almost everything in there is open source. So if you wanted to go in and look at exactly how some of these tools are implemented, some of the algorithms for things like a minimum vertex cover that we have in our tool set, you can go and look at exactly how these are implemented using Python. It's pretty basic and easy to use. We also have, with some of our hybrid solvers, tried to abstract away a lot of the parameter tuning that goes alongside using the quantum computers. So you can kind of choose, do you want to run directly on the quantum computer and really have control over all of those parameters? Or you can try out using our hybrid algorithms where you can really just give it this is the function I want to minimize. Here is my set of constraints, and it will do all of the formulation and everything and all the parameter tuning for you. So really all the way across the spectrum of how much control you want to have over that, we've kind of built all of that into our Ocean tool suite. Yeah. Yeah, so I'm just going to repeat for the people on Zoom. So there was a question about how Q# and other packages work in relation to ours and whether you can use one on other systems. Yeah. Yeah, so right now, unfortunately, what you're seeing is that pretty much each quantum hardware provider is developing their own toolkit for their own systems. So Q# is only going to work with the Microsoft products, and Qiskit is pretty much only going to work with the IBM products. We did I don't know if it's still there or not, we did a plugin to work with Qiskit so that you could use our solver as the backend on some of your Qiskit algorithms. But aside from kind of those little custom plugins and tools, they're going to pretty much be standalone. Yeah. Yeah. So again, so the question was, is there a central project to kind of combine all of these? There's a lot of quantum services or platform providers that are kind of trying to consolidate a lot of this. So you'll see groups like Strangeworks can offer access to multiple platforms. I think AWS Bracket has access to many different platforms. One of the things though that's very different is the gate model algorithms and the annealing algorithms are just structured very differently. So I think even when you have these platforms that offer different hardwares or things that are hardware agnostic, I think a lot of times it would really benefit you as the user to understand the hardware that you're using to really maximize the benefits of using it. Yeah, it's a good question though. Cool. Yeah. So Ocean, like I mentioned, it's in Python. You can use it with a quick, easy pip install in your computer. But we also have an in-browser development environment. So you can go and spin up a virtual environment right in your web browser, run all of your code there. It's very similar to Visual Studio if you've used that. It has a nice visualizer so that you can kind of see how your problem's embedded on the quantum computer. So there's a lot of really cool things there to help you get started through our Leap platform and with Ocean. Launches, professional services, that's really like mostly commercial customers are interested in that. So yeah, we have a team that's really working to examine those commercial problems, look at all of the ins and outs and analyze those and build up custom solutions for those customers. All right, so I mentioned that D-Wave has been around for like 20 years. And so we have produced quite a bit of results along the way. So as I mentioned, we're kind of building up that hardware with each generation. So our last generation platform was the 2000Q, and now we're on the Advantage platform and working on the Advantage 2 platform. Like I mentioned, you'll see on the far right, we're also working on a gate model system. And then in that teal bar along the bottom, we have these hybrid solvers and everything that goes with our cloud platform. Along the way, we're also working on, good academic research in our R&D side, looking at, what are the quantum effects using the annealer? How are they working? What kind of speed up can we get? What are we seeing? And we're very focused on like, what can you do now rather than the theoretical bounds of what might be possible in the future. So we have lots of different publications that we can share with you, both from our teams as well as external teams that look at, whether they're like material science problems, lower level physics experiments, as well as real world problems, looking at commercial advantage for customers, where we're looking at improving how they are doing their processes in their business today and seeing what we can do better. So some of these that are listed here in this orange box in the middle, you see Menton had 100 times speed up. Menton is like a protein design startup that's looking at protein folding and kind of designing new proteins. This was a group that is kind of a small startup that I think came out of the Creative Destruction Lab in Toronto. We also work with like larger grocery chains like Save On Foods, and we look at, their internal processes, lots of optimization problems in retail and looking at what we can do there. Yeah, I'm gonna skip ahead. All right, so let's talk a little bit about the hardware. Even though I'm not a hardware specialist, I find that this is really useful in understanding our model and how you need to formulate your problems. So I'm going to start with our 2000Q system because it's a little bit simpler, so it's easier to see in pictures what's going on. So this is our 2000Q system. So on the right, you see like this golden chandelier that you see with a lot of quantum computing companies that use superconducting qubits. So this is going inside of a massive black box that is going to cool this down to around 20 millikelvin. So for superconducting qubits, we need to get it as close to absolute zero as possible. We want to shield it from noise and all of that kind of stuff. And so that's really what all of this technology in that top right corner picture is doing. And then way down at the bottom, zoomed in the larger picture, that's our sample holder where you can actually see the chip right there in the bottom. Now, if you look closely, and I'm not sure if the resolution is good enough, but you should be able to see a little bit of like a grid pattern. And so if you counted, it would be like 16 by 16 tiny squares on that chip there. Each one of these squares is what we call a unit cell, and this is where the qubits actually live. So in this unit cell, you can see lines going across horizontally as well as vertically, and each one of these is a qubit. It's a tiny loop of metal where the current can flow, and it can flow in one direction, the other, or both at the same time. So each one of these is a qubit. And so you see 4 going across and 4 going down. So that's 8 qubits in one unit cell, 16 by 16 unit cells. And so that gives you the 2048 qubits on the D-Wave 2000Q system. So this is what it would look like if you really, really zoomed in, but you don't normally see it drawn like this. You actually see most of the QPU chips drawn in this way, where each of the qubits is a circle, and a line connecting them means that they are coupled together. On the physical chip, being coupled together means that they cross. So if they cross, then we can put a Josephson junction there. We can basically say, we can have relationships between these two qubits that say things like take the same value or take different values. So here in this drawing, in this zoomed in square, that's like a different way to draw one of these unit cells with 4 qubits going across and 4 going up and down. So each one of these lines means that those qubits crossed, they can influence each other, they are coupled together. And so you can see this big picture on the right is the full 2000 Q chip. One thing that you'll notice is that there are kind of gaps in it. So for example, can you see my mouse there? Yeah. If you look down at the bottom here, I don't know if you can see this, but like around here, there are some gaps. And essentially what that means is that when we calibrated the chip, we check each and every qubit on the chip and make sure that it's controllable to our approved level of precision. And if it's not, then we just kind of like disable it so you can't use it. But next time we calibrate it, it might be fine. So this is how you can tell that this is a picture real chip that was online and was calibrated, is there's some of those missing. This is why we call it the 2000 Q, and we say over 2000 qubits when in fact, if you counted them, it would be 2048. So this is usually how you see them drawn with these circles and the lines between them. And this is important because this is the way you're going to formulate a problem to run it on the quantum annealer. So essentially what I have here are linear terms in the first summation. Those Q's, those are your binary variables. And the A's there, you get to choose those as a coefficient. That's your choice as part of your formulation. You can think about these linear terms like those individual qubits. Then in the second summation, we have quadratic terms. Those are like the qubits that are coupled together. And so essentially when you need to formulate a problem to run it on the quantum annealer, you will have to put it into this kind of quadratic form. This is that quadratic unconstrained binary optimization, QUBO, that you've heard mentioned earlier today. So this seems like a really, really simple form, and it seems like it might not be that interesting, but it is actually quite interesting. There's a lot of really, really hard problems that can be mapped to this form. So there's a great paper done by someone named Andrew Lucas that looked at CARP's original 21 NP complete problems and mapped all of them to this form. So that means that you could take any of those original NP complete problems, map them to this form, and run it on the quantum computer. So right there, right off the bat, a lot of really interesting problems. So essentially you have these linear and quadratic terms because what the chip is made up of is those individual qubits and qubits coupled together. So I mentioned those pictures earlier. That was the 2000 Q system. That system has since been deprecated because our advantage system has over 5,000 qubits. So this is a nice animation that starts with the chimera topology, that last one I showed you. And there you see that unit cell. And now it's going to add a whole bunch of extra things in there. So extra connections, extra couplers between qubits. And that's what the chip structure of our advantage system looks like. So it gets very complex, very hard to see. And the reason for that is because we want those extra couplers. So I think we've heard it mentioned a few times that like one of the limitations when you're running problems on the quantum computer is that you don't have every qubit connected to every other qubit. So the more connections we can make, the easier it is to embed your problems, the better solutions you're going to get. And so that's a big focus of our hardware team, is how do we add more and more of those couplers? Yeah. Yeah. The chip is tiny. Yeah, I mean, it's really like the physical like hardware of the chip and how you do it. Yeah. It can, which is again is what makes it complicated to do that. Yeah. I think there was a question in the back too. No? Okay. Okay, so yeah, as I mentioned, you know, our advantage system, this is our most performant system that we have online. So it was released a couple years ago. And then 1 or 2 years ago, we did like a performance update, which improved the fab stack and everything on there that reduced the noise and all of that. So the advantage system is over 5,000 qubits. It is also the backend, the quantum piece of our hybrid solvers that we have online as well. So this is running every problem that you run on our solvers. It's going to run on one of these advantage systems, the one in the US, the one in Europe, the one 20 minutes down the road. So I mentioned that we also have a prototype of our next generation system. So our Advantage 2 system, our hardware teams are projecting that it's going to be released next year sometime. But in the development of that, we generate lots of smaller chips to check all of the topology and the new structures. And so part of that is that we actually had one that came out really, really good. So we decided to make it available to everyone. So this is a small version. It's only about 500 qubits. But what's exciting about this is it has a new topology again. So we saw the pictures of the CHIMERA, that 2000Q chip. That one had every qubit connected to, I think it was like 8 others. The CHIMERA chip, or the PEGASUS chip, which is the Advantage one, that has every qubit connected to 15 others. And now this new one, our Advantage 2 chip, is going to have a new structure that's going to have every qubit connected to 20 others. So each step along the way, we're kind of adding those connections in, as well as improving, coherence, noise, and all of those other important things along the way. So we have a nice white paper if you're interested in like the specifications and all of that. But this is available online. So anyone that signs up and uses our Leap Cloud platform has access to this prototype chip as well. All right, so I mentioned we also have hybrid solvers. We have a whole class of 3 different hybrid solvers. These are like portfolio solvers where there's a number of different algorithms running behind the scenes. The 3 different forms differ primarily in how you want to formulate your problem. So the first one that we released was our binary quadratic model solver. This is going to run QUBOs like exactly what you ran on the quantum computer, but much, much larger, up to 1 million variables. We then came out with our discrete quadratic model solver. This allowed you to have not just binary variables, but discrete variables. So each variable can choose its value from a set of up to 10,000 choices rather than just 2, 0, 1 for binary. So this was kind of our first step into generalizing that formulation and making it easier for people to use, that their problem might not necessarily fit into that binary format. Then the most recent one is our constrained quadratic model solver. This solver is really, really easy if you're just getting started. This is definitely like the easiest one to start with. This one basically, like, you have your cost function, you have your objective that you're trying to minimize. You have your set of constraints like x1 plus x2 equals 5. And you feed those all in separately and independently, and it does all of the formulation and parameter tuning for you. We have symbolic variables, so you can literally just like type in the math equation that you wrote down on your piece of paper. So it's very, very easy to use. It's also the most general because you can use binary variables, integer variables, and continuous variables. So this is something that we were asked for a lot, was continuous variables. And so we do kind of log those feature requests and put those into account and make it happen when we can. So this one, like I mentioned, it's the easiest to use. It's probably the most performant. I would say our commercial customers are primarily focusing on that constrained quadratic model hybrid solver. So these hybrid solvers, I know for people that are new to this space, it's not really clear what that means, but basically the hybrid solvers take this really, really large problem that is way larger than the size of the chip, and it smartly figures out how to take that and formulate smaller subproblems that can run on the quantum computer. So this is going to run on both classical and quantum resources, all on our platform. So there's a lot of interesting things going on there. So like I mentioned, the continuous variables, this was a really exciting addition. We were asked for this all the time when we were meeting with people. Before having the ability to use continuous variables, it was really, really painful to kind of like discretize everything and fit it into binary variables. You could lose a lot of precision and all of that. And so this really allows you to kind of stick with a more native formulation of your problem. All right, and then the last, most recent addition that we have, we've seen a lot of interest in feature selection on our, using our hybrid solvers. So we have a lot of people looking at different applications of feature selection, whether it's like fraud detection in financial networks, anomaly detection in like computer networks. Feature selection, it's a nice combinatorial problem. So, you have your data, you've got a whole bunch of features and you're trying to choose which of those features are most important. And so you're trying to find the right combination. And so what we have done is we built a plugin for scikit-learn. So essentially the same as you would use any of the scikit-learn existing feature selection tools, you can now just plug in our plugin and it will do the formulation and everything for you and run it on our platforms. So it's a really cool way to kind of just plug it right in and try it out. And not only that, it's open source. So you can go and look at the full formulation and how we're actually constructing that problem to run on our CQM, the constrained quadratic model solver. So there was a webinar on this recently. If you're interested, you can check out on our YouTube channel. There was a full hour-long webinar showing how to use it and some examples there. All right, I think I only have a couple minutes left. All right, I mentioned a lot, we have our software toolkit. So the software toolkit Ocean has a ton in it. So this is just a really quick high level of everything that's in there. So starting at the bottom, basically you've got different compute resources available. You've got CPUs, GPUs, and QPUs. So this could be everything from this laptop that I'm going to run my Python program on to the quantum computers and the hybrid solvers on our cloud platform. Within our software toolkit, we have what we call samplers or solvers, and these are the actual tools that you're going to use to solve your problem and are going to run on those compute resources. So for example, the D-Wave API, that's using the quantum computer directly. The hybrid solvers I've mentioned. We also have some classical solvers in there like simulated annealing, taboo search, different classical solvers. So you can kind of debug and test your code on those first. And so, yeah, we add new solvers, like I mentioned, with those hybrid solvers, they kind of rolled out over time. So you can definitely see additions pop up in this row. Above that, we have our problem formulation. This is really that QUBO or binary quadratic model, or if you're using one of those hybrid solvers, you've got the more general forms. And so our Ocean toolkit allows you to formulate these in a number of different ways. There's lots of different things you can do with those. Above that, we also have some specific packages that are really useful for getting started. So for example, we have a graph mapping package called D-Wave Network X. It's built on top of the Network X package that's really handy if you're doing any graph theory problems. It has built into it a couple formulation functions already for things like maximum independent set, traveling salesman, lots of different things in that area. And again, open source, so you can go and see how those formulations are done. All right, I think I'm just going to leave it at this. I know this is primarily for computer vision, but there are tons of applications in different areas. So this is just a small snapshot of everything that we have and we've seen from different users and customers in a lot of different industries. So tons more information on our website. If you're interested in applications in specific areas, just let me know. But yeah, I would really encourage you to just go and try it and play with it. Our Leap Cloud platform, like I mentioned, you can sign up for free. It's got demos, code examples, documentation, everything you could need to get started, plus more. So yeah, happy to take any questions.
There's time for questions. Yes, Tajun, please.
We should definitely find out. Could you provide a preview on there's the hybrid solver for for that solution that is delivered? To what extent is the quantum side involved? To what extent is the classical side involved? Or even times in user control, I want only the QPU to solve this and go on the classical. Is it possible to do that?
So with those hybrid solvers that I listed, no. So those are like our proprietary industrial solvers, but we do also have an open source package called D-Wave Hybrid that's designed if you want to build your own hybrid algorithms. So it has kind of like a framework where you can insert different blocks for like decomposition. What solver do you want to use to run your sub problems? How do you want to recombine that? And build up like a multi-threaded like kind of framework. So that's definitely something that you could do with that package. Yeah.
We've got another question over there.
Thank you for the interesting talk. Can you say something about the energy consumption of the D-Wave computers?
Yeah, I don't know the numbers off the top of my head, but it's super energy efficient compared to like supercomputers for sure. Essentially, all of the energy just goes down into like cooling the big black box, and there's very little energy required to run it. I want to say the number is like 25 kilowatts, but I don't know over like what time period, but very energy efficient.
For 2000 Q, it was 15 kilowatts hours, like once I read it. Just
Oh, okay. Thank you.
another question.
Hi.
So if you run your software on, let's say, a 500 qubit system, how well does it scale? Is there any way you can find like all the work that you do to optimize or get your problem work on a smaller scale? Does it just automatically scale to the larger qubit systems, like the 512 going up to whatever the new advantage to?
Yeah, no, that's a really good question. So it can be a little bit trickier than that. So when you're scaling up problems, so I think in the first talk, there was a mention of like when you have to use a few qubits to represent one variable. And as you scale up, those like chains of qubits get longer, and that can affect the quality of your solutions. So you may need to do more parameter tuning. You may need to adjust like the anneal time and anneal schedules. Usually as you scale up, it's harder and harder to control it as you use more and more of the chip, basically. So, yeah.
We have one question online.
I think this is me, right?
Yes, please.
Okay. Yeah, thanks, Victoria, for the nice talk and giving us a very nice overview of D-Wave. I have one question. So most of the API that is open to us allows us to submit problems, and I would say usually from a very high level. And of course, it kind of allows us to control parameters or sample solutions. But for example, can we go deeper than that? Can we actually specify how the Hamiltonians are initialized on D-Wave? Because we would like to somehow maybe implement some interesting algorithms that are, that have some kind of physics basis. So to do that, we need to touch the Hamiltonians from time to time, at least initialization of that. Can we do that?
So right now, that sort of thing isn't exposed to external users. So like there are ways to do that our internal research teams have done. But yeah, I get asked for that a lot, and it's not something that we have available right now.
Okay, and if we have a custom project, would D-Wave be able to support, let's say, just give some internal access or just run these models internally for us, kind of?
We'd have to talk. I don't know. I'd have to check with the hardware teams. Like I know they do that because our lab, we have like a bunch of quantum computers and only one is available to external users because it requires a lower level of access than most people have. But yeah, we could talk about that and see.
Great, thanks.
It's not up to me.
All right. Let's thank Victoria once again. Thanks a lot.
Thank you.